So a few years ago, I shot and released a video detailing the quick testing of a mechanical fuel pump, showing a diagnosis based on return fuel line flow partially. I shot the video based on what I was taught as far as how a standard mechanical fuel pump is constructed and its internals. But I've since realized there's some problems with that, and in this video we're going to revisit mechanical pumps and delve more in depth about how they work and diagnose them properly from a technical standpoint. That last video was never intended to be a catch-all and unfortunately has turned into kind of, well, a big thing. And if I search on the internet for mechanical fuel pumps, it comes up, and I don't like the fact that it did it quickly and there's some information in there that needs expanded upon, and it's not totally correct for correctly diagnosing your fuel pump in the end. And I feel like I need to expand on that and make some corrections. So let's get into it. So most, if not all, mechanical pumps being made now do not use a bypass valve and internal regulator. Instead, those that have a return to the tank use a small orifice restriction on the high pressure side that bleeds off pressure when the pump is static. Maximum pressure is mechanically and automatically regulated by an internal spring that is not part of the bypass. We'll see that when we tear down a pump and look at the inner workings later on here. Early mechanical pumps, like this one here, you can see it just has two ports. There's no return. They usually had no return or vent. While this functions just fine to pump fuel, as the maximum pressure is still internally regulated, problems did develop with keeping the higher pressure fuel in the line between the carburetor and the pump with the engine off, and then increasing heat and heat soak as the engine sits there and gets a little hotter as the heat rolls off of it under a closed hood. And this resulted usually, sometimes, in fuel boiling and hard restarts when hot due to vaporized fuel that can't be pumped the same way as liquid fuel, because you can't pump a vapor like you can a liquid. You need a completely different kind of pump. This condition, I'm sure you've heard it, it's called vapor lock, and manufacturers combated this by simply adding a return orifice here that serves to slowly bleed off the higher pressure side back to the tank when the pump stopped running. This has an orifice down in here. It's not as big as the pipe. It's severely restricted. If you look at this one here, you can see the orifice. Hopefully you can see the orifice in the little line there. It's just got a tiny hole in it. Some pumps will have it down in the entrance, and some will have it up at the actual exit. And since it's just a small orifice, when this pump is running, hardly any fuel can go that way because of the comparatively huge volume that the pump is moving past by the pump diaphragm. It just doesn't have much chance to pass any fuel at all. But when the pump is sitting there not running, it provides an outlet path to just slowly release that pressure. This simple adjustment they made mostly prevents vapor lock under normal operating conditions. They're the same inside, it's just this has the tube and the orifice to bleed off that pressure when it's not running. That's really the only difference between these two pumps. So let's look at the broken down one here in some detail. So the parts of the pump, we have a seal here. I've split it apart with an angle grinder. Just, you can't really uncrimp these easy. You can see the bottom part of the casting, and this is the diaphragm and spring. And as this lever moves up and down here, you can see the other end of the arm moves up and down in there, which allows this diaphragm to move up and down if it so chooses. It doesn't force it to, which we'll see later. And there's a spring on each side. There's a spring below and there's a spring above this diaphragm, with the divider being this plate here. So, and as you can see, this moves separately. This whole plate doesn't have to move up. It can move these springs independently, and the diaphragm can never move at all sometimes. And that's an advantage, as we'll see, for self-regulation. So this is the diaphragm that pumps fuel. As it moves down, it sucks in air or more liquid, and then as it moves up, it squirts it out. And that happens because of these little reed valves here. So it sucks in fuel. This is the inlet here. It sucks fuel in through this valve because it pulls that rubber flap down with the suction, and then as this starts to come back up again, it closes this valve and opens this one because this is an opposite valve. This one pushes up. and so it pushes in here, and then of course as the diaphragm starts going back down again, it sucks this one closed and reverses, and back and forth and back and forth. Now sometimes there is a little bit of overlap in there, which we'll see when we get to the actual demonstration of the pump with actual fuel and pressure, and you can see it kind of can release under some just brief moment when that lever arm changes position. These aren't just completely closed or completely open necessarily. They are rubber, and they're not perfect. And when your pump starts to wear, you know, these rubber, they're just rubber flap, you know, rubber reed valves here, these can wear out. And in the first video, that's probably, you know, that's what we were seeing when the pump gets weak necessarily. You can have these weaken, your springs can weaken if they get overheated on an overheated engine, although that's more rare. Your diaphragm can wear out or get a hole in it or something, and then it's not hardly going to pump any at all. So overpressure isn't really an issue with this style pump when used in the proper application, because they're calibrated by these mechanical springs. So this lever sits on a spring, never directly on the diaphragm. If pressure's too high on the output side, the diaphragm won't move, and instead the springs will compress. It'll just sit there, so it's kind of self-regulating. When it reaches its maximum pressure, as declared by these springs, it'll just sit there and not move, and the lever can still move so that it doesn't injure your cam lobe or anything. So the output pressure is governed by the rated pressure of these springs. So if a pump's rated at, say, like 8 psi, that's the fuel pressure which these springs will compress instead of moving the diaphragm. And this is how these pumps are internally regulated. It's really an easy and smart solution. It's all built into the pump and into the internal workings of these systems. The only downside of that is that it's non-adjustable, but on a stock application you don't really need to adjust it. It's going to pump fuel up to where you want. You can get different pressure fuel pumps. You can get high pressure fuel pumps. You know, this lever is going to move regardless as the engine turns, because this lever rides on a cam lobe usually on most engines. It's some part of the engine that will move this lever back and forth, and that's never going to change unless you put a spring in there, which I haven't really seen anybody do, but it's possible they do. I mean, you could. But this lever usually 99% of the time on a mechanical pump is always going to be moving. So all you have to do is make these springs harder to push, and you'll keep raising that pressure up to whatever, you know, the maximum that this diaphragm can provide pressure wise, and the valves can sustain. So now we know how the pump's supposed to work from a technical standpoint and looking inside of it. I've got this test rig hooked up, and we're going to watch it in action. The first thing I'm going to do is, we have zero pressure. I'm going to pressurize this with my pliers here. So as I pressurize this, it should pressurize quickly, and then as I release it, you'll see it slowly bleed down. If you see a quick bleed down like we did in the first video, then that means it's pretty much a bad pump. If you see like an instant bleed down, that's because the internal valving inside is going bad. And that part of the video is correct. So what happens there is you've got fuel leakage through the return, of course, but you've also got a lot of fuel leakage back through your bad valves that aren't holding the fuel in the can like they're supposed to, except for the return. So what I'm going to do now is I'm going to pump it multiple times, and you should see the needle move back and forth, and that's the valve overlap. When I start to press the lever, it goes down quickly and then it springs back up. I guess this pump is rated about 6 psi. See. So now, very slow bleed down, and there's kind of a pause as everything stabilizes. So that's what you should see on a correctly working valve system. As the needle falls closer to zero, it's going to slightly increase in speed because it's losing volume. Fluid dynamics and all that stuff. But up at the top, you should see it kind of hang up at the top for a little bit, slowly start to fall and then increase. And that's the way it's normally supposed to work. Now, as I showed in the first video, if you do have failing valving, you can kind of block off that return, and then some of the return that would have been the return action will be taken up by the weak valves. The problem is the actual pumping part of the pump is also going to be weak because of that, but you can limp. Just like I said in the original video, you can limp a weakening pump along sometimes, just shutting off that return line Don't even remotely recommend it, but if you're in a pinch and you just can't quite get enough fuel out of your weakening pump to get home, you can just throw a valve on there, or, you know, kink the line on the return side temporarily, the rubber part, just kink it and wrap a zip tie around it, you know, like this, to block it off, something like that. But again, don't recommend it. So I mentioned about cam lobes and things like that, but let's talk about pump failure events. You can have a failure of the cam lobe itself where it just rounds off and there's no metal left, so it's just a circle, and your lobe isn't going to move anymore. It has to have that oblong offset oval of some kind in order to move this lever. It can wear down just a little bit, and then this lever might not move as much, and you might be stuck more in like that valve overlap, and so you might not move any, even though this arm still might be moving a little, you might not actually move any fuel at all, because these valves are just trading positions and it's not really pumping anything. The lever has to move significantly in order for this diaphragm to move back and forth. Obviously, as I said, the pump itself can fail internally. You know, this is just rubber. These valves can fail. You know, your exterior seal can leak. It can start leaking fuel. The diaphragm can leak and get fuel down in here, which in turn goes into the oil passageways in the engine. So if you get fuel in your oil, that is one place to look. Other than going past the piston rings, it can go past the fuel pump. And again, this is all rubber, and although it's supposed to be like, you know, modern ethanol rated and stuff, it's not always. Or, you know, these lower quality things we get here. But if you look at these, this is a Carter pump, and this diaphragm, you can see it has this woven, hopefully you can see, it kind of has this woven material in the middle. So this is like a composite arrangement here. It's not solid rubber. It does have some significant backing to it. And of course the springs themselves can fail from, you know, if you severely overheat your pump, you can take the temper out of the springs. You know, like this spring down here, I can't pull it out without disassembling more of the pump, which I'm not going to run that pin out yet, but this spring down here is a lot smaller and a lot closer, and this is connected usually directly to the engine block, you know, maybe a gasket. And so you get a lot of heat coming off the engine through this casing, and so, you know, if you severely overheat your engine, you might want to check out your fuel pump, just because you know, heat can go up here, it can damage the springs, the rubber, everything. Heat is a big killer. You can also get clogged lines. This tiny orifice here, it's very small, but it could get plugged. And that's not so much an issue except for vapor lock, because then you've basically converted it into just a 2-port with no return pump, no bypass at all, no way for fuel to get back. So from that regard, you know, you can check flow rates and things like that to see if anything's plugged up, anything, you know, fuel is moving. You can take these off, you can check that out. You can always check the pump itself by, I'll show you here with a pair of pliers. So you can check the pump itself, and you can check this on the engine as well. Just pull it back a little bit. You don't even have to disconnect the lines or anything, and you can just see if it's pumping just by squeezing this lever. Like right now I can feel air moving. You know, it's pumping air out and it's sucking air in. And that's an easy check to do, especially if you have fuel hooked up. You can see it move, and you can see if it's bypassing too much fuel. There shouldn't be hardly any coming out of here at all when it's pumping, because it shouldn't have much time to come through that tiny little orifice. So if it's bypassing a lot of fuel, that means you might have a restriction or a blockage on the high side, and it has nowhere else to go. And so then you're going to get the pressure that should be coming out here, you're going to get that pressure coming out here. You know, you're not going to have the same volume because it's not the same size tube. So as we have seen, the return side is highly dependent on the orifice size. If you have too large of an orifice, the pump will return too much fuel while running, and too small, it can just clog easily with accidental debris that anything gets past the filters, or contamination from evaporated fuel or things like that. And I just want to note, a pump with an incorrect orifice size from the factory, or if they do something as simple as leave out this little plug here, your pump will return too much fuel and it'll never work right. And I want to note this because a lot of people think, well, the factory would never do that, they have quality control and everything, but parts are getting much worse, and this can happen. It's easy for factories to make mistakes now. Parts are getting junkier, more garbage as time goes on, and just more cheaply made. And so you just want to watch out for that. Even on a new pump, if you say, well, the pump's new, it ought to be working, I got to look elsewhere. That might not necessarily be the case until you eliminate it. I just want to note that there are pumps that appear to have a return, but actually, in fact, it's only an emergency vent in the event of failure of the diaphragm. And these are used mostly in marine applications where you don't want accidental fuel discharge, and it's more dangerous. And the only time that a vent of this type will pass fuel or vapor is when the diaphragm fails and fuel ends up where it shouldn't be, which is on the other side of the diaphragm and, you know, going into the engine. But these pumps, you can tell by where the vent is located. If you look at it, the vent will be on the back side of the diaphragm by the lever, rather than really on the same side or close to the fuel outlet. And that's basically the way that you tell, other than if the manufacturer tells you. But again, those aren't actually a vent. They look like it, but they only flow fuel when something fails. So as I showed, these self-regulating pumps don't have the lever drive arm connected directly to the diaphragm. Pumps that do have a direct connection do require an internal pressure regulator through use of a pressure-activated bypass valve, because otherwise you risk damage when that lever in the diaphragm can't compress or something. It has to be able to compress. There has to be a relief for that fuel somewhere. And if there's no relief, or not a big enough one, then it will cause damage, because something has to give, either the diaphragm or the cam lobe or the lever, and what's going to give is going to do permanent damage. So in those pumps there has to be a passage big enough, regulated by spring pressure, which is normally closed, so that it can vent as much fuel as it would normally pump in one stroke. These pumps, though, they don't need a pressure activated bypass valve, because the diaphragm will always, that lever arm will always be moving, but the diaphragm might not be, because those springs will regulate it. So it basically regulates itself up to the maximum pump capacity based on your engine speed through the use of those springs. The spring regulation is more efficient just because there's less parts and easier to make. You can easily adjust it by changing those springs out, and the only thing you can't adjust is the volume per stroke, but you can adjust that by just making the can bigger, so that the diaphragm's bigger, so that it moves a bigger volume of fuel with each stroke. So that's really the only thing you can adjust with those, you know, by replacing the springs. So I want to address my initial video, in which the main focus was this bypass, and what I got incorrect was the style of pump that we have today, pretty much, where the return is just an orifice restriction and there's not that separate internal regulator circuit with a spring-loaded bypass valve. And I was pretty much always told incorrectly that the internal regulator style was kind of the default that was commonly used, and these orifice types were the really cheap ones that were hardly ever used. And so that was my mistake there. And while the main diagnosis and demonstration of the failing pump valving resulting in a weaker pump was correct for that video, the discussion around the fuel return itself was mainly incorrect for the style of pumps available today. It would have been had that been a bypass pump, and I can't remember if it was or not. I don't think it was. I think it was just one of these standard, you know, El Cheapo pumps. And for that reason, any diagnosis of the fuel return itself in that video isn't really right, but the method of diagnosis for a pump with failing internal valving still holds true, you know, regarding the high rate of bleed down and how quick it was, and the lower maximum pressure that you can increase by completely restricting the return. And with a healthy pump, as we saw, the bleed down after the shutoff should be much slower, rather than a just precipitous sudden drop of the needle, indicating the main valves inside are allowing lots of fuel to flow back all at once. So admittedly, this video is long overdue to correct and expand on my earlier video. I'm leaving that one up because the core of the video is correct as far as diagnosing a failing pump and what that looks like, and a few quick methods to determine that. I hope this video does a good job of accomplishing that. If there's any more info you'd like to see, I can always expand on that in future videos, which I'm sure will be just as boring. Either way, feel free to leave a comment down below. Like, subscribe. It's free, doesn't cost you anything, and helps our channel grow and do more videos like this. And as always, thanks for watching.